All right, I'm pumped. Another physics vodcast. 2 weeks without a vodcast. You're jonesing for it a little bit, I bet. Okay, maybe not. But we are going to get right back into the rhythm of some vodcasts. Some good solid instruction from home. Give you the chance in your own peace and quiet to take notes, digest information so you can come to class ready to go. All right, we're going to use as our springboard for today's lesson the demonstration you saw in class last time. You see that apparatus on the screen. All right, so if you take a look at it, it's the one where we launched a marble and dropped a marble at the same time. Okay, and if you remember, they hit the ground at the same time. What that tells us is that gravity appears not to see the horizontal motion of the launched ball. Right, it pulled both of them down equally. So the really cool thing about this is that we can take two-dimensional motion, right, the 2D motion of the projectile, and we can break it down into two 1D problems. Okay, and the cool thing about that is we already know how to do 1D kinematics. So on the screen you see I drew some blue arrows, and those represent the vertical velocity of the two marbles at each point in time. And notice that, okay, to the best of my ability, the two blue arrows have the same magnitude, the same length, right? In other words, gravity's pulling on them vertically in an identical fashion, and therefore at each point in time they have the same vertical velocity hitting the ground at the same time. Okay, what we want to do now is we want to add in the fact that we know that the launch ball, right, we determined this earlier in the demonstration, that the launch ball actually moves faster, and that's because the launch ball, in addition to its vertical velocity, also has a horizontal velocity, okay, like that. Now, what do you notice about the lengths of the green arrows that I'm drawing? Okay, are they growing like the blue arrows grew? Absolutely not. They are staying the same length, okay? Remember, for something to get faster and faster in a particular direction or slower and slower, it has to have an unbalanced force on it. And I would ask you, what is the unbalanced force in the horizontal direction? Nothing, right? There's no push or pull in the horizontal direction after the launcher pushes the ball out, right? Notice that we're talking about the ball once it's in the air. So notice that in the x direction, in the horizontal direction, there is no acceleration, okay? Whereas in the vertical direction, there is the same acceleration as all free fall projectiles, and that is negative 9.8. So we can write that as follows. Perhaps I'll stick to the color coding, right? So we'll say a equals 0 in the x direction, but in the y direction, right, a equals negative 9.8 meters per second squared, right, just as usual. Okay, now if you look back at the launch ball, okay, it has both vertical and horizontal velocity. Those are two vectors, right, acting at the same time, and therefore we can combine those vectors. If you notice, they're at right angles, right? They are friendly vectors, and we know we can combine them by doing the Pythagorean theorem. Now what I'm going to draw is I'm going to draw a third arrow, okay, color-coded red, and what it does, this color-coded arrow represents the total velocity of the ball at any point, okay, at the different points in time. All right, now I want you to notice what's happening to the length of that red arrow. Okay, I'm trying to be a little consistent here. What do you notice about the length of this red arrow? It's growing, right? In other words, as you probably already know, the marble as it falls speeds up. Okay, it's speeding up because its vertical velocity is speeding up, and therefore its total velocity is increasing, right? So we could summarize the velocity changes by saying that the vertical velocity increases because of gravity. The horizontal velocity stays the same because there's no push or pull in the horizontal direction, but the total velocity increases because the vertical is increasing. Okay, a few more random facts that we've mentioned in class that I want to emphasize to you. The path of a projectile is that of an arc. Specifically, it's a parabolic arc, right? It's that of a parabola. Okay, it's also the path of a projectile is called a trajectory. All right, so these are some vocabulary words that you want to be familiar with. What I'd like to show you now is how we're going to take this concept and apply it to some problem solving. Okay, I've switched screens, all right, and you should see hopefully you're not groaning right now, but perhaps you are. You're seeing your familiar kinematics equations. But what I've done is I've broken them up into a horizontal side and a vertical side. And I've written the same equations on each side, okay? And remember what we're going to do, the way we're going to tackle 2D motion is we're going to make it two 1D problems, okay? And that means that the kinematics equations can be used in either direction, and you really have to you have to be clear about which side you're working on. Either you're working on the vertical dimension or the horizontal dimension. You can't mix and match, and that's why I've drawn a big dividing line down the middle, okay, so that I can be very clear about whether I'm working on the X side, right, or the Y side. Okay, I want to be always clear about that, and that's why I make two columns, okay, and I'm going to ask you to do the same thing in your work. Now, there's some things that we can fill in here, okay. In other words, the next step here is to begin to identify our variables, right? We're going to skleps this problem, okay, and we're going to have the same variables here as we did in 1D kinematics, okay. Now, think about what we're going to do is marry our 1D knowledge from last unit with our newfound projectile motion knowledge. Okay, one of the things you know is that there's no acceleration in the x direction, right? So on the x side, a will always equal 0, which means if there's no push or pull in the horizontal direction, that the final velocity and the initial velocity will always be the same number, correct? Let's go to the y side. Okay, on the y side, we have a similar, right? We have the same set of numbers. So this can get really complicated because now you have, like, if you thought this was a lot of letters last unit, look how many units you have now. Hopefully you will buy into my dividing your paper into two columns. It's really going to help. Now on the y side, you know about that motion as well. Okay, you know that the acceleration is negative 9.8. Right, so on the y side, it's always going to be negative 9.8. Okay, the key to solving projectile motion problems is to recognize that there's only one variable that goes on both sides of these columns. Okay, there's only one variable that's the same on both sides. Can you guess which one it is? Thinking. Well, if you guess time, right, you are correct. Okay, you are correct. Time is the one variable that's the same for both the x and the y direction. So typically, almost every single projectile motion problem, what you will do is you will solve for time on one dimension, right, on one side, and then you'll take that number and you'll plug it into an equation from the other dimension. Okay? All right. One last thing here. If we go back to the x side, you're going to notice a few things. If we go back to these equations up here, okay, because the acceleration is 0, you're going to find that this goes away, right, because that's times 0. And this goes away because that's times 0. And this goes away because that's times 0. And what you're left with, right, is you're left with the final velocity equals initial velocity, which you already knew, so that's not even an equation. Okay, and then up here, same thing, right? You're left with the final velocity equals initial velocity. That's not an equation, really. It doesn't give you any new information. You already knew that. And so what you find is that the only equation that you use on the x side, because there's no acceleration on the x side, is this one right here. Okay, so let's scratch these out a little more clearly so you can see, right? So on the x side, right, to simplify this process further, you're only going to use equation 3 from the board, and even that is a simplified version. All right, what I'd like you to do is to have this written out in your notes, and we're going to use this exact problem right here that you've written out the beginnings of. We're going to use this to solve the speed problem of the projectile bus the next time you come to class. All right, we'll see you soon.